Hi, my name is Ahmad Mohamed Azim, and today we would like to present our project, which is a 1-bit magnitude comparator. Our objective was to design a circuit that compares two single-bit inputs, A and B. The theory goes like this. The first thing is A is greater than B. As you can see in the truth table, if A is greater than B, then the result is 1. Only if A is 1 and B is 0. So the Boolean logic used is A and B bar. Second is A less than B. It outputs only 1 if A is 0 and B is 1. The Boolean logic is A bar and B. And the last one is A equal B. The output is 1 for both if both inputs are 0 or both inputs are 1. So the Boolean logic is A XOR B. Okay, let's see the schematics. Okay, here is a inverter schematic we design using Cadence. Next is NAND schematic. Okay, on the right side is our NAND schematic. It has two inputs, and the last one is XNOR schematics. Okay, this one is XNOR schematic. So top level schematic, we done by instantiating these standard cells at the top level. We assemble the complete 1-bit comparator logic. Okay, next.
My name is Yongshen. Before drawing any physical polygons, we ran a pre-layout transient simulation using Spectra. So this gave us our idea baseline. As you can see, the waveform are perfectly sharp, confirming our truth table logic is mathematically sound. So there are two inputs, the three outputs, same as the truth table. So let's see the first line, the first column, A is 1, B is 1. So A equal B is on. So others are off. With the logic verified, we move to physical design. We drew the layout for each standard cells manually, carefully sizing the PMOS and NMOS transistor and managing the M-well and P-substrate boundaries. So there are three layout we have to draw before moving to top level comparator layout. So this is an inverter layout, one inputs on a poly and one outputs. And this is NAND gate layout. So up there VDD, down there ground. There's two inputs, A and B. So there's one outputs of the NAND. And moving to XNOR gate. This is the XNOR gate layout. Up there are the pull out network, and down there is a pull down network. So for XNOR gate, there are two inputs. So the first two columns are the inverters A and B. So with the first inverter, the output will come up with A bar, and the second inverter will come up with B bar. And there are one outputs for this XNOR gate. Then with this three layout, we will have one top level comparator. So this is the final top level comparator layout. We then use layout Excel to generate this top level comparator. So we also use the apartment technique to seamlessly share the VDD and GND ground rays across all cells to save silicon areas. For routing, we establish a strict layer direction using method 1 for short vertical connections inside the cells, and method 2 for horizontal signal highways like our A and B input tracks. We prevent short circuits.
Thank you, Tim. My name is Faris Amnuddin. Moving on to verification. Before you can ever confidently send a chip design off to a foundry for fabrication, you have to verify that your physical layout is manufacturable, accurately and structurally prepared to handle real-world physics. We did this by running a strict three-stage verification within Cadence, which is design rule check, layout versus schematic, and finally parasitic extraction. First, we ran a design rule check on every single CAD cell. Design rule check acts as our automated physical enforcer. It systematically scans our geometric drawings to make sure they strictly obey the foundry's manufacturing limits, checking critical parameters like minimum wire width, exact layout spacing distance, and area constraint for the 90 nanometer process library. We were happy to report that our design successfully cleared this stage, returning a clean, no DLC errors found notification window. Next up was the layout versus schematic check. While DLC only checks our physical geometry, layout versus schematic digs into the electrical netlist. The software mathematically extracts the actual electrical connection from our physical drawings and stacks them directly against our original schematic. Passing this milestone with schematic and layout message was a huge win for the group. It verified that we didn't have any accidental short circuits or missing connections, proving our layout was structurally identical to our logic. Finally, we perform parasitic extraction. An ideal schematic simulation assumes wire have zero resistance and capacitance, but real silicon doesn't work that way. Parasitic extraction bridges our ideal logic with physical reality. The software mathematically abstracts all the microscopic unintended resistance within our method racks and the parasitic capacitance that occur when wires cross or run near each other. By compiling these parasitic values into a highly detailed abstracted view, parasitic extraction gave us the exact electrical model we needed for our final post-layout testing. Ultimately, clearing design rule check, matching layout versus schematic, and abstracting our parasitics gave us the absolute green light that our design was ready for realistic simulation.
Thank you, Faris. My name is Muhammad Ibrahim. For our physical design work, we can run a post layout simulation using the expert view. Looking at the result, the core logic still hold the truth perfectly across all four input states. But if you look closely at the output transition, you can see this tiny voltage spike of logic twist. Furthermore, the edges are slightly rounded compared to our layout simulation. This is the physical proof of the RC propagation delay caused by the wire routing we just showed you. In conclusion, we successfully drove a 1-bit comparator from a theoretical schematic all the way to an LDS3, or the static accelerated layout.